Great. And I got sound on, so if anybody has anything to say, you can just shout it out. That's great. Okay. So where we left off was talking about data silos, right? And with data silos, the problem is you have a lot of data in your organization, but it exists either isolated from other databases, or you sometimes have copies of the same data in different places, and problems can arise. For example, if you have data that's referencing the same thing in two different places, and one of them gets updated and one of them doesn't, or one bit of data is erroneously tracked in one database, not in another, these are sort of things that can happen. It's a problem. A simple example from the dawn of the internet era, right? So 30 years ago, if you wanted to place an online order for something, right, you didn't just do it over the regular internet, right? Most cases you couldn't. Some businesses had proprietary EDI, electronic data interchange, but mostly if you wanted to place an order for something, you got on the phone and called them. You talked to, Susie at the front desk, and Susie would say, oh yeah, okay, I'm gonna talk to people in operations, I'll forward your request, and the people in finance and accounting, they'll look at your information, and we'll get back to you in 3 to 5 business days with the terms of, possible transaction. Now, that was fine in 1993, but once everything's online, people want to be able to go to a website and right there find out what the terms of the transaction are going to be. But if you have this sort of database silo problem, data silos, what would happen is you don't know the state of your account because that data is in a different database with different permissions. So you'd have to see, first of all, how much credit do I have available? And they got to do some calculations to figure out what the terms are going to be, how much interest they're going to charge. Do they demand a big down payment or no down payment or something in between, right? And again, those sort of requests have to be in some sense handled by hand because there are different people in charge of the different databases. It's not all integrated together. The other example we gave, of course, was with oil drilling. And again, if you want to do some big whole operation type question, if you have all of these local databases, they're going to be different. You're going to have to write a unique query for each of them and then somehow tabulate and compare the results in some sort of standard format. Okay, so data silos they lead to a lot of problems. Part of it's performance, part of it is the possibility for errors, and part of it is just it's a real headache to do anything across those databases. So we might fairly ask, well, gosh, if you know data silos are going to be a problem, why wouldn't you just integrate all your systems from the start? Well, for one reason, businesses start out small. And when you're a small business, you're mostly concerned with staying afloat, right? Making enough money to keep going. You're not thinking like 10 years down, oh gosh, we better have all this database stuff in place so that when we get really big and are serving hundreds of millions of customers, we're all set for that, right? That's not how a little business starts out. Typically, operation only happens in one place. You got a single employee in charge of what might seem to be multiple silos. For example, you might have one guy who does the finance and accounting and the bookkeeping, even the marketing spend, right? They might do all of that. And sure, those would technically be different databases, right? They might be stored in different files or, whatever, different applications. But because it's all under, the hand of one guy, he has everything he needs right there, right? It's kind of not really a data silo for him. And even if it was, there's just not that much data when you're starting out. So all the problems that happen with scale, like the fact that cross checks for accuracy in your databases are going to take a long time, that's not a big deal when you're starting out, right? And if there is a mistake in your database, well, you probably just pencil it, change it, fix it, update it pretty quickly. Now, of course, the other thing that happens, sometimes a business acquires another business, and there's no way that you're not going to have data silos for a while in that event. Because why? Because the other business already has all their databases set up however they want to have them set up, and they're not going to be set up the same way as yours. So data silos are a problem that you can't entirely get around. It does happen. So the way the businesses deal with this is ultimately they put all their data into a common system so that all the data in these different databases is in the same format. So for example, in our case with oil drilling, they had a bunch of different things for mineral types, equipment, whatever. Every one of those organizations would have their database fitted to some standard format. And then if you wanted to ask the database a question, you could write one query for that one big table that now includes everything else. Now, making that happen is a big headache, right? It's a lot of work. Back in the 90s, you would routinely see, so the software for that is what's called Enterprise Resource Planning, or ERP. You'd routinely see organizations spending a few $100 million over the course of a couple years to get this stuff up and running. So it's not a trivial thing for a big organization, but you need to do it. And in fact, there was a big wave of ERP installations in the 90s. At this point, everybody who needs it pretty much has it. So all the big businesses have it. Pretty much all the medium businesses have it. Even some small businesses do because it's useful. Any small business that hopes to get bigger is probably already having that. But yeah, in the 90s, you would read these articles in the, Wall Street Journal or wherever, because we still read newspapers in the 90s. You'd, say, oh, Kmart spent $300 million on a failed ERP attempt. It was just a train wreck. In fact, when I was starting out in grad school, my first year, 04, that's what I wrote a paper about ERP type stuff. So for what this 40-page, term paper about ERP. So I used to know a little bit about it. Anyway, now I know what ERP stands for now. All right, the rest of, okay, so questions about any of that? We covered data silos. I tried not to run it into the ground, but, data silos are bad. You fix them, problems can happen. You fix it by basically having ERP, which means bringing all your data into a common format. Okay, nothing? Okay, well, the rest of today is about what's called data mining. So data mining is very simply finding patterns in data. So organization has a big pile of data. They want to answer some questions with that, find some patterns. So the classic way data mining used to be done is for all of those advertisements that you would get in the mail, right? So Target sends out a catalog every month. They got to look at different zip codes and try to figure out, oh, zip code A is interested in this set of items. So we'll craft our catalog to include those. Zip code B is interested in a different set of items, right? And if they're really fancy about it, they might try to pin down individual households as far as, whatever in terms of their demographics and other attributes. So they would, different houses could get a custom, somewhat custom catalog, right? They're not going to make one catalog different for every house, but they're going to come up with a dozen or 24 catalogs, and they'll try to figure out which group you belong to so that they send you the catalog that hopefully works well for you. Okay, so that's a very simple thing that data mining used to be done, and it still is. All right, so all of these patterns, all right, some of them are useful, some of them are not. Businesses need to look for patterns that provide ways they can make money. Now, some of you may have heard the story about beer and diapers. Anybody heard about beer and diapers ever? It's not as famous as it used to be. So some of your marketing guys, when they talk about data mining, they might think this is a funny thing to bring up, and they'll talk about how there was a company that was doing data mining, and it found that the surprising result that beer and diaper sales were strongly correlated. A lot of people who go to the store to buy diapers are also unusually likely to buy beer. And you might fairly ask, well, that's interesting. Can we make a lot of money off that? Probably not. I mean, you don't want to be the store that, puts up a big display that says, above the diaper says, we know you got kids, you're going to need beer, right? And put the beer in diapers. It's not a good look. Anyway, what the story with that, though, Osco, Osco, that's the drugstore side of Jewel these days. Osco had like 5,000 SKUs. So SKUs, SKUs, they're basically product codes. SKU is the standard term. So they had like 5,000 SKUs, different products, and they wanted to thin that down, right? Because it was getting to be a hassle dealing with different suppliers and this and that. And so they wanted to simplify. They wanted to try to figure out which SKUs they could get rid of without having a significant effect on sales, right? So they were looking for ones that they didn't sell a lot of and weren't highly correlated with other products. And they happened to notice this strong correlation between beer and diapers, right? So it's the narrative that has come up around it is that, sometime it's 10:30 on a weeknight, and the wife says, hey, we're running low on diapers. And the husband's like, but it's 10:30, I'll get them in the morning. She's like, no way, man, what happens if we have a diaper blowout overnight? And he's like, oh, fine, I'll go get some diapers. So he gets in the car, goes out to Osco, and while he's there, he's like, hey, here I am at like close to 11 o'clock on a weeknight buying diapers. I'm getting some beer too. So That's the narrative. But can they really make a lot of money on that? I don't see how. Another link there if you're interested. It's also about beer and diapers. Talks about people who spend, organizations that spend a lot of money on this kind of data mining, only to realize that the results they get aren't terribly useful, right? You can always find interesting correlations that may, in some cases, make for fun stories, but unless it's data mining you can actually make money off of, it's not really that useful. Now, Target, about 10 years ago, they used to do this neat thing. So I don't know if any of you have ever been around pregnant people, but when a woman gets pregnant, there's a bunch of product categories that she's unusually likely to buy. And Target noticed this. So when Target found that people were going to its stores and buying these products, Target said, we think you might be pregnant. So we're going to send you a little basket of goodies and coupons and stuff, right? To say, Target's here for you. You know, we know a baby's on the way and that's great. So here you go. Now, the fun part begins. There was a girl in high school. I forget her age, probably like 14 or something. But anyway, she gets one of those baskets from Target because she has been buying a lot of those products, right? Enough of those products to trigger Target's auto delivery of the goodies basket. So her dad is very upset. Her dad gets on the phone with Target and starts yelling at their manager saying, I can't believe you would do this, and that you're saying that my sweet innocent daughter who would never have sex until well after she's married is, you know, doing that thing that you said she did. And a few months later, of course, she had the baby. And Target decided that, you know, it would be great if every baby was a planned and joyous event. That would be a wonderful world to live in. But unfortunately, it isn't always the case. And so they kind of backed off doing that. So they made it an option that people could like join into, but you know, they don't just auto send out this stuff anymore because again, yeah, people might not be real pleased. So that's some data mining stuff. Now, the field of data mining itself is a very big field. Some of the main points in there, number one, statistics, right? There's a lot of math involved in trying to figure out what products are correlated with what other products. Algorithm design, trying to figure out ways to get the machines to do the calculations that you want them to do. And then computer programming, trying to convert those algorithms and statistical rules to actual functioning computer code. So if you have an interest in any of those things, who knows, you might end up doing some data mining one day. Now, of course, most business programs do offer some courses in data mining. UIC is no exception. We got a few. And those courses will generally give you a little bit of theory. They'll tell you about some of the math behind it. And then they'll give you like a batch of data and you'll try to find whatever interesting thing you're supposed to find in there, right? Way back when I took data mining here, we used a program called Minitab, which is visually very similar to Excel, but you know, it's designed for data mining stuff, not just spreadsheet stuff. And of course, you're only going to get the tip of the iceberg, right? Data mining is a huge field, and even if you take like 2 or 3, you know, 16-week classes, you're not going to get that much, right? This is the sort of thing that, you know, you're in it for years and you learn as you go along and all that. So just for IDS 200, I'm going to introduce a few major techniques, talk about them. So let's do it. First one is regression analysis. Anybody take statistics and has done regression analysis? Anybody? Yeah, okay, cool. All right, so we had one person in the morning class as well. So regression analysis, the idea with that is you have some variable that is a function of a set of other variables. So the other variables are called the independent variables because they're not really dependent on anything. The one that's the outcome is called the dependent variable. So you basically have a bunch of variables that in some sense determine the likely value of the dependent variable. So an easy example is hot dog sales at a ballpark, okay? So suppose you're running a hot dog stand at Wrigley Field. What are some factors that you can think of that would tend to correlate with higher hot dog sales? What do you think? Yeah.
Number of competitors?
Well, there's conventionally 2 baseball teams.
I meant like amount of hot dog people selling it.
Oh, okay, very good. Yeah. Yeah, okay. Good. Because you have to filter them out. Yeah, what you got? Yeah, how many people are in the stands, right? More people, all else equal, more hot dogs. What else? Yeah. For sure, right? Well, I'm not exactly sure how the whole situation is going to work, but I'm sure weather's a factor, right? You could just as easily say, well, if there is rain and attendance is high, the game's going to go on longer. It'll get interrupted by rain, people will be longer there, they'll get hungrier. So I don't know how it's going to play out, but would weather be a probable effect? Sure, right? What else? Yeah, maybe advertising has an effect somehow, right? And you could think about other stuff that might have a factor, right? Like the number of dudes you got going out through the stand selling hot dogs versus making people wander up to the hot dog shack itself. You might say the location of the hot dog place, right? Because it could be anywhere in the ballpark. Uh, and the obvious one, if it's a doubleheader, right? Because if it's a doubleheader, they're playing two games. All those people are there twice as long. Probably going to sell more hot dogs. Just saying. Okay, so in this case, all the factors we talked about, those are our independent variables. Hot dog sales is the dependent variable because it depends on the value of all those other variables. Okay? So that's good. Now, this is not a math class. So we're not going to do any real math. You won't have to do math on the exam, but I'm going to give you an example of regression analysis. Okay, so our problem is we have an auto manufacturer that wants to produce some profit maximizing number of cars. Now it's got to produce a bunch of cars because those assembly lines aren't cheap, and you got to pay for that whether you make 0 cars or 10 million. So they want to make some cars. But on the other hand, they don't want to make so many cars that at the end of the year they got to deep discount a bunch of them to get them off the lots. And they don't want to make not enough cars so that they're leaving money on the table, right? So they're trying to figure out what's a good and sensible number of cars to sell. And suppose that their number cruncher guys have crunched a bunch of numbers and have found out that there are 4 variables that explain a whole lot of what the optimal number of cars to produce is. One of them's gas prices, one of them's domestic GDP growth, one of them's consumer confidence, one of them's interest rates, right? And we can talk about those. So in the model that I have on the next page, gas prices are actually higher gas prices lead to more sales. So maybe this is a manufacturer that makes hybrids or something, right? Or electric cars. So if gas goes up, people are going to buy more of these alternative cars. GDP growth in general, is the economy doing well? If the economy is doing well, people are more likely to buy cars. Likewise, consumer confidence, right? If ordinary people feel their personal situation is pretty good, they're a lot more likely to buy a car than if they're nervous about the future. And finally, interest rates, right? If interest rates are very high, borrowing money is more expensive. Most people who buy a car don't just show up with a suitcase full of 50s to buy it. They, go on some kind of payment plan. So having higher interest rates increases the real cost of the car. And so people are going to be less likely to buy a car because, it's more expensive. All right. So that's the narrative, right? But the important thing is they've actually looked at these numbers and they found that this is actually the case. So what they do, they crunch all those numbers and they get a set of independent variables. Okay, and each one of those independent variables has a significant effect. I'm going to put this in Word. Just a second. If I can find Word, I should be able to find Word. An average person would be able to find Word. I know, it's got to be here. So what the hell? I don't like Windows 11. I'm still getting used to it. All right. I know. Okay, good. So this is what I wanted to do, and I'm going to put this in Paint. Bum, bum, bum. Let's make that. Oh. Yeah, Canberra guy. Okay. That's fine. Boom. 18, 20. There we go. Okay, now you guys can see it, which is what all I ever wanted. Okay, so the way you express this kind of regression equation is at a line, right? So you guys, I think the way they probably teach lines these days is y equals the intercept plus bx, right? And that's what this is. So y, I'm gonna just label some stuff. Y is the dependent variable. And we don't need 20 for that. We'll bring it down to 16. Okay, so y is the dependent variable. Alpha, that screwy looking A there, is the intercept when all x variables are zeros. And the betas, those are actually capital B's. If it were a real beta, it'd have a little tail on the B, but it's hard to put in PowerPoint, so it looks screwy. So I just went with B's. X variables are the independent variables, and the betas are multipliers for them. So basically, beta means how much a unit increase in x causes y to increase. All right, so for example, in this equation, if x0 goes up by 1, then product b0 times x0 is going to go up by b0, right? Because you've added another unit of x, which means, to keep the equation correct, y is going to go up by b0. So the short version, bigger betas mean a bigger impact on y. Okay, and that's what we're doing here. So again, machines do all this work. You put in a bunch of numbers, they'll do a bunch of analysis and figure out which variables make sense as explanatory variables for y, and then you'll have that. It'll give you the model, right? You push in the data, it gives you, potentially a set of possible models, and you pick one, but the machine gives you the model. Now, if you want to apply that, then it basically becomes a plug and chug kind of problem. So we're going to put this in Notepad. So our formula, right, if we do this here, I'm just going to follow along with what's in the slides. There we go. So y equals alpha. Oh, I can just paste it in for, yeah, boom. Okay, so y equals, we have the alpha is 500,000. Okay, gas prices, the value is 3, the beta is 30, so 3 times 30K, plus domestic GDP growth, value is 3, beta is 15K, so 3 times 15K, plus consumer confidence, the value is 50 and the beta is 5,000, so 50 times 5K, plus finally interest rates, value is 5, oh, I gotta do a minus, 5 times 25K, right, because it's negative 25,000 on that beta. We do the crunch of the numbers, 500K plus 90K plus 45K plus 250K minus 125K equals 590, 635, 885, 760 if my math is right. 760K is what we get. Okay? So, regression analysis, you have a bunch of data, you come up with some linear equation type model on it typically. There are other nonlinear models, but typically it's done as a line, and then you get the answer. Okay, that's what regression analysis is. All right, next one we're going to talk about correlations. All right, so in this example, you're running a video game store. It's like a GameStop or something, okay? And you want to see which video game products tend to be bought together. And your relevant data, the data that you're putting into this system, is a year's worth of video game system and accessories purchases, right? So consoles, controllers, steering wheels, keyboards, and of course, games. And you end up with this. So all the numbers down there are for per 1,000. So the way to read this chart, the number in each cell is the intersection of the two things, the column and the row for that. Now, if the column and the row are the same, like in the upper left, it's consoles and consoles, that just means 250 out of 1,000, 25% of the time, somebody's coming into your store and buying a console. Likewise, the lower right, the intersection of games and games, out of all your 1,000, on a typical batch of 1,000 customers, 800 of them are going to buy a game. Okay, everything else is an intersection of two things, right? So, for example, consoles and controllers. So, out of the people who buy consoles, 100 of them are going to buy controllers. That's what you see on average. Okay. Now, with this kind of model, you get 3 important types of information: support, confidence, and lift. So support is very simply just how likely is it that 2 items get bought together. For example, we can look in our chart and we see that out of every 1,000 customers, 100 of them are going to buy a console and controller. So the probability of buying a console and a controller is 10%, okay? Which is not that high, right? Compared to a person who buys a controller and a game, 250 out of 1,000 or 25%, much higher. All right, so we'll talk about what these are used for in a moment. Confidence is what's called a conditional probability. It just means the probability that some item is going to be bought given that another item was bought. So for example, we go back to our consoles here. We say, okay, of the people who bought consoles, 100 of them bought controllers. So if we know that somebody bought a console and there's 250 of those, there's a 100 out of 250 chance, or 40%, that somebody also bought a controller, right? So the confidence of buying a controller, given that they bought a console, is 40%. That's what a conditional probability is. And the last one is lift. Lift is the increased probability of buying some item given that X was bought. So, simple example, let's look at games. So we know a lot of people that are buying stuff at your store, they're buying games, right? 80% of the people that buy something, they're buying a game. Now, if we just look at consoles, we could say, okay, consoles. Of the 250 people who bought consoles, 200 bought games. So 200 divided by 250, 80%. So you might say, wow, that's a pretty high, confidence. That's pretty high conditional probability. But that's just the same as the baseline. If you took any batch of random customers from your store, there'd be an 80% chance that they're buying games. So the fact that somebody bought a controller doesn't really mean anything in terms of greater or lower probability that they're going to buy a game, or that they bought a console rather. On the other hand, look at something like keyboards. So keyboards are an unusual purchase. You find that only 5% of your customers are buying keyboards. But among those 50 people who bought keyboards, 30 of them also bought a controller. So, and controllers, people, there's a 30% chance that somebody buys a controller from your store. But if you know that somebody bought a keyboard, you know that there's a 60% chance they're going to buy a controller. A person who buys a keyboard is much more likely than average to buy a controller, okay? And lift captures that. The lift on that is going to say, yeah, if you buy a keyboard, you're a lot more likely to buy a controller than than a customer that we otherwise know nothing about. Okay, now, where are these things used? Well, items with high support, those are like the very common purchases in your store. And so that's what people are coming to your store to buy. And so it makes sense to have those together to streamline your operations, to be able to serve them together quickly, right? So, for example, McDonald's in the early 70s noticed that a lot of families were going to McDonald's and for their kids buying the same batch of things, right? A small sandwich like basic hamburger and small fries and a small drink. And McDonald's says, wow, that's a really popular combination. We're going to bundle that up as a product, throw a toy in the bag, and call it a Happy Meal, right? And they sell lots of that. Or all of those other type, if you say, I'll have the number 4, McDonald's has done some number crunching and figured out that, yeah, this is something that people order a lot of. So they save time at the, at the register by not having people have to say, I guess I'll have a Big Mac, and what kind of fries come with that? You'll just say, I'll have a number 4. Boom, done. Okay, so again, helps streamline their operations. Okay, high confidence, one thing you might do with that is if you know products are very often bought together, you might train your employees to recommend add-ons or be more knowledgeable about different product categories, or you might even decide, if items are often bought together, you might co-locate them in the stores, right? Set up the displays fairly adjacent. So, for example, if you know that a lot of people that are buying keyboards are also buying controllers, you might have your, your sales associates and whoever's, working that part of the store, if they're selling keyboards, they should know enough to recommend controllers. And maybe it makes sense to put, the keyboards right next to the controllers in the store because people are going to, there's a good chance they're going to buy one. All right. Finally, lift, right? So a high lift is a way of differentiating between two products that are really unusually likely to be bought together, or just, well, everybody's buying this thing, so you're going to show up with a high confidence. So, for example, 80%, 80% of McDonald's customers buy fries, right? Which is probably not too far from reality. Then if you identified that someone buying a Big Mac has an 80% probability of buying fries, it doesn't really tell you any useful information, right? Except that, yeah, Big Mac is about average in terms of buying a fry likelihood. However, suppose it's a very pronounced combination of a fillet of fish and an apple pie for some reason. And you at McDonald's identify that even though only like 5% of your customers are buying fillet of fish, and only maybe 10% of your customers are buying apple pies, of the people who are buying the fillet of fish sandwiches, 80% of them are buying apple pies. And then you say, wow, this is something interesting, right? People who buy the fillet of fish very often, are much more likely to buy apple pies. So what do? Maybe you set up some equipment together to take account of that. Maybe you develop some combo scheme that you can advertise, right? You do buy 2 fillet of fish, get 2 apple pies, something like that. But the point is, you recognize with Lyft that it's an unusually popular combination. Okay. Next thing is clustering. So suppose that you're on the board of a scholarship committee and you are giving out scholarships, but you only want to give them to students who are very likely to graduate. Because why are you sending people a bunch of money, right, if they're not even going to finish school? So you have this whole batch of data that you use to figure out who is likely to graduate, and you've crunched the numbers, and you found that the 3 important determinants are high school GPA, high school attendance, and extracurricular participation, right? So this isn't just you making this shit up. You've actually gone through and crunched some numbers and found that this is the case. People who score well on those metrics are more likely to graduate. And we're going to represent the universe as this box. All right. What the hell? Okay. Now, just a little bit of, we'll put in our stuff. So blue dots are the graduates, right? Students who graduate. Blue dots are students who graduate. And red dots are students who drop out. Okay? So we have all of this data, and we're going to draw a line through the thing, and I'm going to try to capture a lot of this. Let's see how well I can do here. A little bit of work I can get some. Yeah, there we go. We'll just leave it like that. That's fine. Okay, so this is the data, right? So on this side, mostly students graduate. Okay, and then on this side, students mostly don't. All right, and the axes of this cube are those 3 variables. So I'm just going to mark them down. This one is GPA. The y-axis is GPA. The x-axis is attendance, and then I'll do one more for the z-axis. I'll just do back here. This is extracurriculars, so I'll call that XC. Okay? And students who score well on these things, they end up in that part of the cube where there's a lot of students who graduate. Okay? This is what cluster analysis is. You take one batch of data, you somehow spatially divide it so that one kind of result is on one side, the other kind of result is on the other side. Okay. So to repeat that, that's how clustering works. Now, the one that follows is trees. And tree analysis is like cluster analysis, but it's basically more fine-grained. It's like a sequence of cluster analysis operations applied to the data. So here we're going to talk about bank lending, right? So bank wants to minimize its risk of loan defaults by identifying which customers are riskier than others. Okay, simple proposition. So of course, most people do pay most of their bills back and pay off most of their loans, but in banking, even like a 5% default rate is pretty substantial, right? That could wreck their business model. So they got to be pretty careful with lending. Now, the relevant data, again, they've crunched a bunch of numbers. They found this all to be true. So you could build a narrative around it. But the point is they don't really need a narrative because they've done the work and they found that this is the case. And what they found is that income matters, debt to income ratio matters, right? So if you have more debt relative to your income, that's not great for paying back loans. Work history, people who have a stable work history tend to, just generally have more stable cash flow. And of course, age. Age is, for some reason, also found to be important. Now, when they first do this analysis, they do like a cluster analysis on the first thing, and they find out that maybe people with relatively high income, greater than 75,000 a year, are substantially less likely to default than people with lower income below 75,000 a year. Okay? That's fine. That kind of makes sense. It's easier to pay back your loans when you have more money. So, okay. But if they dug a little deeper with this tree analysis, they would identify, there's a subset of higher income people that has trouble paying back loans. And those are the people with a high debt to income ratio, right? So imagine if you have a whole bunch of credit card debt and you're just barely sort of paying that off, it keeps getting bigger. And then for some reason, there's an interruption in your employment, right? That's going to be real bad. Whereas if you don't have much in the way of debt, even if there is an interruption in your employment, maybe you can get by for a while. Okay, so they crunched the numbers and they found out that yes, high income people with a low debt to income ratio, very likely to pay back loans, but there's a subset of higher income people that are, also pretty risky. Likewise, on the other side, again, most people pay back their loans, right? So on the lower income side, maybe they look in and they see people who have 10 years or more of work history are pretty good credit risks. Why? Because maybe they're not rich, but they're stable, they're working, they're responsible. They're the sort of people who try to pay back their loans. And they might identify that, even these lower income people who are not making bags and bags of money, if they're stable and good workers, then okay, they turn out to be pretty good risks as well. And they might find that people who have less than 10 years of work history are much riskier. But even with that, they can dig a little deeper, and maybe they find that people who are young, right, people who are under 28, it's entirely possible that somebody who's been in college for like 5 years is not going to have a tremendously long work history at that point, right? And it's also possible somebody who's older, right? Suppose you're like 50 years old and your life has pretty much been a mess and you haven't had steady employment and you only have a like 5 years of actual verified work history. You probably dropped some balls in your lifetime and maybe you're not such a great credit risk. Okay? So that's what trees are. Trees are this sort of sequential cluster analysis. Now, if we're going to draw it out in here, let's do it, right? We would start off with something like this, right? We would first say, now I'm not going to draw the four-dimensional stuff, but we would first start by saying high income and lower income, not as high, whatever. Okay, that's that side. And initially you would say, okay, this side is green, good risk. This side, not so much, right? But again, like I said, we dig a little deeper and we're going to find some things, right? So on this side, maybe we actually find, high, so low debt to income ratio. And over here, right, this one, high debt to income ratio is actually pretty risky on this side. So again, we're kind of doing sequential clustering here. Likewise, if we did this thing, right, we put in a line here and we said something like limited work history, right, that stays red, but solid work history, right? I guess I got to fill up that with green first. Is actually a pretty good risk, right? And this one, limited work history, maybe if we split that again, we could do that, right? So I could do something like, whatever. So down on this side, maybe I say young versus old, right? And on the young side, even though they have a limited work history, maybe those people end up being pretty good credit risks after all. So I'm just going to fill it with green, but there you go. That wasn't supposed to happen. There you go. Okay, so tree analysis, in effect, it's kind of this sequential cluster analysis, which gives you much more fine-grained control over the whole analysis process. Okay. Now, last point, ethics. So about 20 years ago, Enron, what's the word I'm looking for? Very publicly crashed and burned. And one of the things that academics saw as contributing to the whole rotten business culture of Enron was that a lot of top business schools were emphasizing competition and ruthlessness and not really talking about ethics at all. And there was a lot of people out there who felt that, yeah, you know what, maybe we need to include a little bit more discussion of ethics and generally being a good business person to help prevent things like Enron from happening and to help prevent that kind of toxic culture. So after that, it happened at UIC and many other universities. Every business course, at some point during the course, made a little mention of ethics. And so here we are. This is where I'm going to do it. So as far as model building, right, all of this kind of, I want to go back to the college admission, the scholarship one. Bring that back. There we go. Okay. So in this case, remember, they've crunched the numbers and they've identified some factors that are shown to lead to good outcomes, right? But you can see over on the students mostly don't graduate. There's one person here who beat the odds. They did graduate, even though they had like a weak looking profile. And over here, there are several students, several red dots, who even though they had a seemingly strong profile, right? They dropped the ball there for whatever reason. Maybe it was their fault, maybe not, I don't know, right? I don't know the stories of these dots. But what I can tell you is model building has a lot of art as well as science. So what happens when you run this sort of regression analysis or other kinds of data, you get a lot of potential options. So if you're building a regression model, what you're going to have is a few variables that are very clearly important in building the model, and then some other ones that are marginal judgment calls, like, do I include this one or do I not? And so the variables you include, the variables you don't include, there's a certain amount of human control over that. Likewise, variable weighting, right? Including which ones are important and which ones aren't important in your model. So for example, in that, right, the way this model is drawn here, it looks like GPA and attendance and extracurriculars are all about equally weighted. And you might fairly ask, well, I can see how we're going to measure GPA and attendance, but what's going to be our scheme for measuring extracurriculars? Are academics more important than sports? Does it matter if you're like an officer of a club versus just somebody there? Say you played football. Does it matter if you're a star quarterback versus being a bench warmer? And how do you track that? Okay, so there are a fair number of questions built into this. And last, the historical window of the data, right? How far back in time are you looking? Now, all these organizations that are doing, your college scholarship board that's doing this, if they have some idea in their mind of what a scholarship student is going to be, and their model keeps giving them that, they're probably not going to see anything wrong with the model. But again, there are all sorts of alternative things that with a little bit of consideration, you might say, hey, maybe this model doesn't capture everything that's important, and maybe everything it captures is not important. So, for example, what are some reasons why a student might be a good student and responsible and all that, but still have a relatively low GPA? What's something that might be, a mitigating factor there? Yeah, go ahead, shout it out. Sure, mental health, right? Maybe they got some troubles, right? I feel like in the last few years since COVID, about half the students have like low-grade ADHD at this point. Not just students, like a lot of people. Things are kind of messed up now. What else? Good. Anything else? Why might a perfectly responsible and good student still not have a great GPA? Yeah, maybe they got to work. Maybe they have to, right? Maybe they have to help keep their family afloat somehow. The other one that I like to say, maybe they're ESL, right? Maybe they just moved to the country from a non-native, English speaking background. They can speak well enough, but it's a lot more work for them. Okay. And so, yeah, their grades aren't going to be maybe great that first semester or that first year. Uh, what else? What about extracurriculars, right? It's nice that somebody's playing football, I guess, but what's something that, could very reasonably take the place of extracurriculars? What would be something that a scholarship board might look and see, wow, you're not playing sports, but you're not just, binge watching Real Housewives either. What's something good you might put on your application? Sure, internships, right? Anything that's kind of impressive that way. So, for example, some high school students actually start their own businesses, which is cool. I had one student several years ago who had a business that they went around, did real estate stuff, and they estimated whether people were trying to keep up with the property. Like they'd gone into default, but he said, you know what? If people are living there and they're trying to take good care of the property, there's a lot better chance that they're going to eventually catch up with payments, as opposed to if, they clearly left and the grass hasn't been mowed in 2 months, stuff like that. So yeah, starting a business, right? What else? Anything else? Like volunteering maybe, or yeah, stuff like that, right? So the point is, when you have this stuff, yeah, the model is what it is, and you can definitely point and say, yep, our model gives good results. But the question is your model the best model it could be? And it's always worth looking into that. Just saying. Okay, I guess that's time. I'll see you all next time. We'll do the next lecture, so please read the lecture notes ahead of it. And then, yeah, we'll see you then. Bye, everybody.